So let's start again. Next we have Leonardo Braz with Hansen Linux for real-time workloads with KVM. Go ahead.
Sure. Hello, everyone. Well, this presentation is kind of a recycling of the previous presentation where I changed something that did not quite go as well as intended last year. And I also added some extra things to make it more easy to absorb the knowledge. First of all, from the people around here who knows about real time and have some knowledge about the topic, could please raise your hands? Okay, awesome. Then I will try to go faster in the first parts. Well, the idea is to improve Linux for real-time workloads. And this year I added KVM because we are also talking about that. Well, who am I? My name is Leonardo Braz. I work at Red Hat in the VRIT team. I work mostly with the Linux kernel. I improve real-time, CPU isolation, and guest latency. And as a side quest, I try to improve RISC-V architectural code. You guys can find me at Leo Braz at IRC, GitLab, GitHub, and a lot of other networks. That's my usual handle. Well, I will start with the basic part, real-time. Then what is real-time? And I will try to describe that with a very short phrase, which is basically, I need you to deal with this request in T-time, or else bad things will happen. That's the main idea of real-time, okay? Now the formal description. Real-time is, in computing, is the term that we use for hardware and software systems that subject to a real-time constraint, for example, from event to system response, which is the most usual thing. You have a request and you have to reply in given time or else, right? They must guarantee response within the specified time, which is often called deadline. So you must not miss the deadline or else bad stuff happens. Why does it matter? Well, missing a deadline have bad consequences. So you have a system you needed to respond in this time or before that time, or else bad things will happen. For example, in a hard real-time system, you have that missing a deadline will cause total system failure. Let's say that you have a pacemaker in your heart and you miss the beat, and well, that may not be that good, or else you're in a hospital and you have this machine that is monitoring life, and well, maybe you may not want to miss that deadline. You have like firm real-time, which, well, you can miss one and another deadline and it will not crash the system, but that deadline will go to waste. And the soft one, which, well, you may miss and the system will degrade its quality if you keep missing them. So deadline, to be more clear here, is you have a request, you have your real-time system or slash workload, you have a request or event, you have a response or result from your real-time workload, and this response time is the time that you take to reply, obviously. And the deadline is the maximum response time for that given workload or that given system needs the reply. So if you miss that, that's bad, okay? Like I said before, hard real-time systems, you have like pacemakers, robot surgery, well, we don't want to mess with that. Industrial process controllers, also you may like have to stop the pipeline if something, if you miss a deadline, and that costs a lot, so you don't want to have that. And for soft real-time, you have something like audio systems and video systems, like you are on a meeting, an online meeting with video, and you lost some packages. You want that to be like as synced as possible, but if you lose packages, it's not that bad. And of course, video games, let's say that you are playing that game and it's competitive and you miss a click, you click and it does not respond, it's not good, you degrade your experience. So that's a way of showing that soft real-time exists around our lives. Well, you want it to respond in a given time. What is the shortest, simplest way of doing this? You have a CPU, you program it directly, you don't add any operating system, and well, you can very easily have this response time very well set on your CPU, and unless you have some hardware failure, you are guaranteed to not miss any deadline if you do that correctly. That's because you don't have operating system to add overhead. But, well, using operating systems is much more comfortable. You don't have to keep implementing drivers. You don't have to deal with creating your own routines. You can use standard libraries and so on. So, yeah, it's good. Abstraction, drivers, libraries. Well, aren't there any OS that are focused on real-time workloads? Yes, there are some. FreeRTOS, Zephyr, RT-Linux are some examples. And each of them has to compromise in some way to be able to achieve real-time performance. Zephyr, for example, has a very simple kernel. FreeRTOS have some weird ways of allocating memory, more complex ways, and it will depend on what are you using. And RT-Linux, for example, this image is better. It just runs a thread with Linux, and your real-time workload goes here, which is bad because you have all the stress of implementing a lot of stuff for your real-time workload. But then you have this VM, let's say, running Linux, where you can like deal with network and something that you don't actually need to be real-time. But your real-time workload, you have to implement that on the platform, like in the system of RT-Linux. You can just like pick your application and just like the one that you design on Linux and or other operating, and just move it to RT-Linux. It's a different operating system. Well, what about Linux? Why can't we use Linux for as a real-time operating system? It's the major free operating system in the market. You don't have to pay royalties to use it. So why not? Well, it was not planned as a real-time operating system. It's more focused on performance, so throughput. You are not necessarily need to do that work in given time, but it's preferred to like use your computing power as efficient as possible, and you focus on throughput at this point. It does not have deterministic behavior. Like when I say that, I say like the one that you just installed, like the vanilla Linux distro. Sorry, my throat is bad. And well, of course, you are running your real-time workload there, and it can be interrupted by the scheduler or the kernel or anything that's considered more priority, and will cause like missed deadlines. So we don't want that. Let's say you're like with your surgeon robot and you're controlling it, and then operating system stops because it has to schedule an idle task for some reason. You don't want that to happen because you miss that deadline, and that can be fatal. As one of the major OS availables, it has access to many programming languages. You don't have to be constrained on the language that's supported on given platform. It has libraries, tools. It's much easier to develop and debug code on Linux than it is to do that on like bare metal systems. It has extensive support, libraries, the sources available. You can like change and add some stuff. You just add the things that you need. You don't have to rewrite the whole stuff. Well, but to be able to use it as a real-time operating system, some changes are necessary. The first one is scheduling policies. Well, we have like this fair scheduler in Linux that gives everyone a time slice and tasks don't get stuck. Well, but we are running real-time tasks, so we want to run our real-time task first before any other task, because ours is more important. Ours have to deal with the deadlines, right? We have something that's called performance schedulers, such as sched-other, sched-batch, sched-idle. These are the ones that are normally enabled in Linux. They are focused on performance in throughput, not how fast can I reply this, but how many replies can I have every hour, let's say. That's performance focused. But there are real-time scheduling policies like sched FIFO, sched round robin, and sched deadline. What they do, they raise the priority of your task and make it run first, as the first slide. Sched FIFO, first in, first out. It all starts with priority. The highest priority task will be run until it ends or until it gives the CPU time to another one, like sleeping. But given the same priority, let's say that you have two tasks with the same priority, you run the one that was inserted first until it's finished, and then it will run the one that was inserted last. Okay. Round robin does a kind of different. I mean, the priority part is the same, but it gives a time slice for every one of those tasks to run. Then it runs for this time slice task 1 and then task 2. I have an image here. It's better to understand. And sched deadline, where you have to pass, like, this task has this deadline, so it will order the tasks in order of, like, I don't want to miss the next deadline, so it has its perks. It's interesting. This one here is sched FIFO. As you see here, it was inserted in this order, so task A will run until it finishes, then B, then C, then it will go to the other priority list, D, E, and F. Round robin, it's a given time slice, so it will go through the highest priority first, so run A, B, and C. A was not finished, so runs again A, B, and C, and so on and so forth until it's finished here. And then you have D, E, and F started. Even though D was inserted like before B, it will run after because the priority level is different. So you cycle inside the highest priority level that has tasks for running. It will like add time slices and keep running until the tasks are finished. And the deadline here, you schedule stuff like this deadline is T plus 0, T plus 1, T plus 3. So then what is the first deadline? Then we will run until it's finished. Then the second deadline run and it's finished, and so on. Preempt RT. What is preempt RT? Stop the kernel, run my task. You have this real-time task. You have the kernel. Kernel has to do stuff. We are not neglecting it. But our task is more prioritized. So we want the kernel to stop running if we have something to do with our task. Give CPU time to it, so we don't miss the deadline, right? It's a kernel option, it's a compile option, where you enable a fully preempted real-time kernel. What is preemption? You interrupt given kernel, like given task, to run another task which is more priority. Usually the kernel is not preemptible at this level, so this function here this option here will enable the kernel code to be interrupted by user space code. How it does achieve that? Replaces locking primitives that would like hold the CPU for long. It will replace them with CPU like locking mechanism that will allow sleeping. The locks get preemptible, so let's say that you can't get this lock and continue, then it can be preempted at this point. And by changing this, you allow the kernel to be mostly preemptible, except some entry code and some interrupt that are very low level, so you can have a lot of control over that, but that's mostly hardware stuff. How does preempt RT improve real-time behavior? Well, if the kernel can be interrupted, you can interrupt this to run your real-time task. And if you run the real-time task first, the chance of missing a deadline is smaller, right? Because you are trying to give for this task as most CPU time as possible, as early as possible, right? That's an example of how that works. I mean, this is without preempt RT. So let's say you're running your user code and then scheduler goes on, switches to kernel code, and you have this real-time request. You have to reply as fast as possible, but it finishes running the kernel code, then the schedule is out and runs the user code. With preempt RT, what you have is like you receive the request, schedule out the kernel code as fast as possible, and then run the user code. You see that here it finishes running much earlier than previously, right? Like this one finishes running the user code before this one, so it replies faster. Okay, another concept that's very important for achieving a good real-time response is CPU isolation. What does it mean? You say at boot time, don't run stuff on these CPUs. You pass a list of CPUs and say, don't run stuff here unless I tell you so, right? How does that work? You pass this parameter to like the command line of booting Linux kernel. There are other options that also use the CPU isolation to avoid running the tick. I will explain more about that later, but the tick is a periodic interruption that allows the scheduler to run. I mean, you're running your workload, and after some time, your scheduler needs to run, or else like you will starve the other tasks. So this scheduler is necessary at this point. What does CPU isolation change? An isolated CPU that you selected in boot time will not be selected by the scheduler to run any tasks. So how do you use these CPUs at all? You have to pin them. You just say on your command line that you want to run this task on that CPU that is isolated. What happens then? It will run like mostly alone on that CPU because nothing else is supposed to be running there. Also, let's say that we have some housekeeping tasks that the CPU must do to keep running. Most of them can be moved to non-isolated CPUs and thus providing more CPU time to the isolated CPU to run your real-time task, right? And this improves the real-time behavior because there are less stuff interrupting our task, so it has more CPU time, so the chances of it not missing the deadline are bigger, are great. This is how CPU isolation is supposed to look. This here, you don't have a CPU isolation parameter. You have all these 4 CPUs to schedule stuff in. So then, well, of course, the scheduler will divide these tasks over the CPUs that are available. You run this command here, you are isolating CPU 1 and 3, which means that you have to run your tasks CPU 0 and 2, which means that the scheduler by itself will allocate all the tasks on those CPUs. And of course, when you pin a task, you can select the CPU where it's going, so you can pin the task to the CPU and it will run mostly alone. Okay, another feature, which is also very interesting, is no hearts full. What we want with that? If my task is running alone on given CPU, don't run the scheduler. Okay, why we need to run the scheduler? We have multiple tasks, we don't want to starve any of them. So after some time running given task, the tick will happen. The scheduler will check if there is not any other task running. And if not, it will continue the previous task. But if it does, it will switch to the other task if it's necessary. But this interruption for the scheduler to check will steal some CPU cycles. And that may cause us to miss deadlines. So, as I explained here, the idea is to turn off the tick if it's just a single task on that given CPU. Offload some other stuff, other callbacks, and it's built to enable it. You have to enable this option in the building of the kernel. What does it change? Disable the tick, no scheduler running for a single task, less interruption, more time to run your real-time task. Right, I'm just trying to explain here, less interruptions, better CPU. Okay. This is how no hertz full should look like on a timeline. You have your user code here and scheduler, and this is no without no hertz full. Scheduler will interrupt your user code, and at some point you may receive a request before the scheduler kicks it, or just after the scheduler kicks it. So you have to wait for the scheduler to finish and then process your request. If you have no hertz full and a single task running there, you have that user code is never interrupted by the scheduler, and when you receive the real-time request, your processing is much faster. Okay, very nice. A lot of concepts, very dense topic. Why does it matter for us? We want numbers, right? For these numbers, I measure latency. What I'm measuring is the highest latency perceived by each of the CPUs in the system. So I will show an average and a higher number. And both of them are the average of the max latency of each CPU. And then the max one is like the highest latency latency CPU has. Okay? We use cyclic test, which kind of does something, sleeps, and then go back and check if the sleep time was the one that it was requested, and takes the difference and counts as latency here, which is good for checking predictability. OSLET is much simpler. It is just like reading the current time in a loop, and when it gets interrupted, well, you have a delta between the previous time measured and the next one, and then you just subtract them, and the biggest value of this run is captured as maximum latency, okay? Stress energy is just to create noise on the CPUs to test if the CPU isolation is working and the scheduling is working, okay? Cyclic test. It was run on a CPU with system with 20 CPUs for 12 hours. The case here is no other workload. We have an average latency of 4.57 microseconds, and the higher one, I mean, from all the CPUs, the maximum latency of them summed, like average, is this value, and the CPU which had the highest latency is this one, 8 microseconds. Let's say that we have this isolated CPUs, that you have workloads on the even ones and the cyclic test on the odd ones. You still have this latency, or what does this mean? Even though you have like influence between the CPUs, the latency still keeps very low. Now let's say that you have non-real-time tasks running in those same isolated CPUs, and they are competing for CPU time with cyclic test. You still have like 31 microseconds of latency, which is still pretty low. Now OSLET, okay? With no other workload, you have like 2 microseconds, which means that your user space task, when it was stopped, like you will perceive the latency at most 2 microseconds. This other case here, the higher one is also this, which means that you don't have that much difference between the highest one and the lowest one. The same state, like we have workloads on odd and OSLET running on the even CPUs. We have this average of 2.1 microseconds, and the higher one is 3 microseconds, which is also very low. This is not tested with workloads in the same CPU because, well, OSLET is like reading the time every kind of cycle, like every 3 cycles it will read time. So it's competing. If it's competing for CPU time with other tasks like stress, it won't behave well because at some point stress will have CPU time. So that's not what we want because it will like measure a lot of latency. Okay, what's new in this presentation apart from the numbers? Real-time and virtual machines. What we want is something like this. You have the preemptor RT enabled, the isolated CPUs, no hearts full, and you use these isolated CPUs to power KVM threads, which create n virtual machines, all of them with the same features enabled, like preemptor RT, isolated CPUs, and no hearts full. And we measure the latency on that workload and on that workload running here. Okay, let's just be clear. They are not sharing CPUs. You will have some situation like CPU 3 goes to this one, and CPU 4 goes to this one. Okay, that's the whole idea. Like we have a huge machine with a lot of CPUs, and you have like, oh, those CPUs will go to this virtual machine, and those are going to that one virtual machine. Why? Why do that? The motivation is the same as regular VMs. We can have less computers, more efficient computers, more powerful computers, and not like have at all distributed computers around. You can like focus them. You can migrate them much easier than if you are running like on bare metal. And well, you can have cloud providers providing you a VM with real-time capabilities, and well, it can enable a lot of stuff that wouldn't be possible if the client would need to like purchase and configure a real-time system. What are the drawbacks of using virtualization? Overhead, which adds to latency. You have guest entry, guest exit. Preemption. If you have preemption, it may happen like on host and on guest, which is kind of weird because like the host don't have vision of what's the priority of the task that's happening on guest. Okay. And well, you have housekeeping. You have the kernel doing housekeeping work on both guest and host. Also, if you centralize your machines on a single place, for example, you have to take into account the latency of the network. I mean, the information has to go in and go out, so you also have to take that into account. For this scenario here, this VM, I collected some numbers. You have for OSLET, you have like 14 microseconds as an average of the max, right? And for the higher one, like the CPU with most latency, we have 23 microseconds. It's still pretty low. Cyclic test, same idea, 24 hours running, 8 CPUs. It has an average of, like with stress, both of them with stress, not on the same CPU, but on adjacent CPUs. You have an average of 15 microseconds, and the higher one is 18 microseconds. So for 24 hours, the CPU which has an event with the most latency had 18 microseconds with competing tasks on other CPUs. And that's what my teams work, reducing those numbers so it can be available on for more applications, and we can use that and we can service people with this ability of doing real-time tasks. That's some of my work in the last couple of months. Added trace points for scheduled functions. It helps us to find which part of the kernel is violating our latency requirements. Also, avoiding isolated CPUs. I mean, as I said, we want to avoid using the isolated CPU as much as possible. So there are some works that we need to do to avoid doing housekeeping stuff there. Not always is isolated at this point. For the KVM part, we have like RCU, which has to run at some point, RCU core. There are this case where it was running exactly at the point that the guest exits. So we use a new, we propose it and use a new instruction that is a patience, RCU patience, that enables us to note a quiescent state and avoid RCU core to run for a couple milliseconds after the guest exits, and that's time enough to go back to the guest. And I'm currently working on changing the local lock strategy to avoid IPIs. What are IPIs? you have a processor interrupting another processor to do something. Some scenarios that can be avoided. I mean, it's pretty efficient when you're not talking about real time, but if we can avoid that interruption on our real-time workload, that's good. That's what I'm currently working on. And that's it. I hope you guys enjoyed, and I'm open for questions.
Any questions?
First of all, great presentation.
Thanks.
I would like to know how I would go about using this real-time version of the kernel. For example, let's say I want to replace characters in a F32 with Linux using this way. Is there a way? Is it easy?
Yeah, well, the first thing I would do is like try to see if that platform that they're using supports Linux. Yeah. That's the first part, okay? Then you can just see if they are they have this real-time version of Linux. If not, you can compile yourself. I mean, support is complex because it may or may not work. But at Red Hat, at least we have those platforms that are like verified and that they supposed to work. Those were used to collect those numbers, for example. After that, you can just port the application to run for Linux, and the application is just as any other application. You will try to work them thinking about real time because, well, your application has to be designed for real time, but you just would have to rewrite it. But it's most interesting if you're starting a new project, right? Because it doesn't make much sense. You have a project that's already working to like port it to another system, unless you have this necessity, okay? But for a new project, that's pretty good. It will speed up a lot the development time and debugging time and so on. That answers? Okay, thanks.
Going back to what I showed previously, there is the upstream Linux R3. And for instance, if you're using a rel, if you wanted to go for rel or something like that, you would grab the config of an RT kernel, and you could build on top of that, on top of the upstream tree.
Oh,
So it's already a base ground.
Yeah, if you have, if you want to use rel, you have this kernel like ready.
Merchandise.
Yeah. Purchase. What?
About the numbers that you show in the presentation. For example, if I designed an application that it's supposed to be real time.
Okay.
It's easy to measure the same numbers or to measure latencies or?
It will depend on the system. As I said, if you are using a system like the ones I use it to, yeah, you can run that will replicate, the numbers will replicate at the system. We are guaranteeing this. Whenever those numbers do not replicate over some threshold, we receive a bug and we have to deal with that. So if the platform is verified, you're good to go. You can trust those numbers, okay?
Just a quick question. You say you want to reduce the delay number, right?
Yeah.
Is there a goal, like a tangible goal, like 10 microseconds? I don't know.
It will depend on the applications. Like say, we have a client that wants to be a little lower than that's our target, okay? But as a general rule, if we can reduce this latency as much as possible, that's better, right? So the smaller, the better latency, right?
Okay. And what's next in the roadmap?
Oh.
I think we talked about it a little bit before, like
Okay.
TCP,
Yeah.
those stack part.
Yeah.
Is that on the roadmap?
Well, my focus at this point is on kernel. When you say like about user space code, what you have is like there are tools, there are libraries that are specific for like doing network on real time. Okay, for example, you have like the PDK, which is like user space network, so you don't have to rely on interruptions, so it's faster. So you are probably wanting to use this, but on kernel part, I mean, in my vision, that's what we need to do, like avoid APIs. That's the thing that's sucking more of our latency at this point.
Okay.
Thanks for asking.
So going back to the diagram that you have,
Which one?
this one.
Okay.
How do you guarantee that the isolated CPU in the guest will interrupt another guest if its deadline is approaching?
Come again?
So you have deadlines in real time, right?
Yeah.
You have to comply with them.
Okay.
Let's suppose that vCPU number 4 on the VM on the right